Well, there's obviously a lot of text on this slide, but all of these are very good points to keep in mind in distinguishing these two mechanisms, and I've said most of this already in the previous videos here. The last point at the bottom, though, is one I want to expand upon a little bit. The SN1 reaction is faster, and normally that's better, but it does suffer from the limitation that because it's so fast, it's sometimes hard to control. And as it says there, with an SN1 reaction, the nucleophile usually ends up being whatever the solvent is, because many common solvents, like water and alcohols, make decent nucleophiles themselves. With SN2, you can plan a little bit better to not only have the reaction occur at a particular carbon, the one where the halogen starts off at, but you can control which nucleophile is actually added and substituted. And as it says there at the very bottom that's underlined, a big difference between these two mechanisms has to do with the stereochemistry of products if you start with an alkyl halide that is chiral. And that is what I meant in a previous video when I talked about these two mechanisms sometimes leading to different products. It really leads to differences in the stereochemistry of those products. So on this slide, if we imagine this alkyl halide here to be chiral, if those four colors represent four different atoms or four different groups, then that would be a chiral molecule, one of two possible enantiomers. Be it R or S, it would depend on certainly the exact identity of these groups, but when the SN2 mechanism occurs, the nucleophile comes in from the opposite side that the green atom here leaves. And so what that means is it essentially reverses the chirality at that center. We say that there's this inversion of configuration. So for example, if this alkyl halide were an R isomer, then it tends to produce an S isomer, even though it is a different chemical product, different name. We have changed the atoms after all. But as far as the configuration around that chiral carbon, it is the opposite of what it starts off as. So if you plan ahead with a chiral alkyl halide, and if we know it's going to go SN2, then we can anticipate how the chirality of the product will be affected. And normally when we have chiral compounds, we like to have either one enantiomer or the other. Oftentimes naturally occurring compounds, if they are chiral, then nature prefers one particular handedness. It prefers either the R or the S isomer, but not both. So oftentimes when chemists are creating compounds with chirality, they like it if they can get a single enantiomer. And SN2 substitutions have that advantage. If you look at the bottom, the SN1, it scrambles the chirality. If we start with the exact same enantiomer, but if it were undergoing an SN1 reaction, remember the first thing that happens is the leaving atom leaves and creates a 3-bond positively charged carbocation, and it is not chiral, or it is achiral is the fancier term. And so now the nucleophile, whatever it is, can come in from either side, and you tend to get this 50-50 mixture of both enantiomers. We call that a racemic mixture. And so we kind of lose that chirality, so to speak. At least we lose having a single enantiomer in our reactant. It becomes a 50-50 mixture. And like I say, generally when we make things that are chiral, we, for the most part, tend to want to avoid making racemic mixtures. Usually we have in mind to make one particular enantiomer. And so SN2 reactions are usually more valuable in that regard, even if they are a little bit slower.